Okay. Start quiz. Open up Excel. So you said that last week you're somewhat familiar with Utah, like New Provo and how Spanish Fork wasn't too far away. Do you have family in Utah, or did you used to live here, or have you just visited a lot?
So I used to visit a lot, and I also have my whole dad's side of the family is in Utah. So I have grandparents in Provo. I have a brother in Orem going to Utah, UVU. I had another brother go to law school in Utah, and I have literally all my aunts and uncles on my dad's side live in Utah, and my dad grew up in Spanish Fork. So
Oh, okay.
yeah, so yeah, I have some ties in Utah, but
Yeah,
what
I
one
just
doesn't?
I just forgot to ask you that last week because you mentioned that, and then it was just in my mind. It's just kind of like, yeah, everybody knows Utah, and then I stopped and like, well, she's over all the way like on the other side of the country. Not
Yeah,
everybody who doesn't live in Utah doesn't live in Utah moves from Utah. So it made me
yeah.
stop. I'm like, yeah, family visited, just went to EFY like every single year for 6 years. Like,
I when I went because I used to be an on-campus student at BYU, Idaho,
mhm.
and I hated it, but so I would always go to Utah on the weekends. That's another reason why. But yeah,
A bit of a drive.
it is a drive from Rexburg to Provo. It's depending on who's driving. I drive pretty fast, so I can get there in like 4 hours. No, 3.5, something like that. Yeah,
That's
three
not too
hours. Three
bad.
hours to Salt Lake, and then another 50 minutes to Provo or so,
That's
depending
like
on traffic, I guess.
yeah, that's practically like driving down to Vegas and back every weekend.
Yeah, I put a lot of miles on my car. Not bad actually, but
Hey, you do what you got to do.
yeah. But all right. Okay, so do you have the quiz up?
Yes.
Okay. All right. Find the margin of error for.
Oh, I have a question for you, real quick.
Okay.
So, you know how, so we find the standard deviation
Mm-hmm.
by going sigma divided by the square root of n.
Yes.
Sigma represents the standard deviation of the population.
Mm-hmm.
And since we're usually trying to find stats about the population,
Mm-hmm.
because they tend to be unknown, where do we get sigma?
Um. Okay. We get it from. Is this something we learned in this lesson?
It was mentioned offhandedly,
Okay.
but I was just reading it and I was like, things are going to get messy before the end of the semester.
Yeah. Um. Uh. How do we get the sigma? Hmm.
They have to give it to us.
Okay. Yes. There we go.
So, in
That's why
order,
I always kept saying, if it's known, then
yes.
do this. If it's known, do this type of
And so, yeah, so that just opens up a whole can of worms
thing.
because the thing is, we are estimating one population parameter
Hmm.
based, like, with all the stuff that we're doing, we're given ridiculous amounts of information. Like, here's the sigma, and this is exactly what sigma is. And we're going to give you a huge population size, like n equals 1,000 and stuff, and we're still only estimating mu.
Hmm.
And so I just wanted to give you a heads up that there's going to be a point, I believe, where they aren't giving us sigma, and we
Um,
have to estimate sigma the way kind of like we're estimating mu right now, which means that our estimations of mu are going to be even more off because it's going to be an estimation based on an estimation.
oh my
So
gosh.
that's why like you're seeing this stuff and you're just like, oh, why are like political polls so off? Like we have the math. This is so simple. Like you have to realize they're giving us like kindergarten stats right now. And like when you're in real world stats, it's estimations based on estimations, based on assumptions, based on estimations. And they
Oh,
do pretty good. They do pretty good.
uh-huh.
But yeah, it's I just wanted to just wanted to
Prepare me.
yes, put that in the back of your head just for because it'll
Yeah.
probably pop up by the end of the semester. I know that like Sister Cook's been really good with not just bombarding us with like new things, like everything's kind of building on top of it.
Yeah.
But just keep that in the back of your mind because most likely it is going to pop up before the end of the semester. And so our standard deviation,
Uh-huh.
well, I should say our sigma is going to be an a assumption or um, what was the other word I used? Assumption or an estimation. And
Okay.
sometimes when you're dealing, yeah, I remember this was literally the thing that made me change majors from biochem to molecular biology.
Oh my gosh, so sad.
Because, and I know they sound exactly the same, but biochem, biochem was insane. Molecular biology was nice. Really, like the only difference between the two was that biochem was in the chemistry department
Mhm.
and molecular biology was in the bio department.
Mhm.
I got along a lot better with the bio teachers, so that was one thing. And then
Mhm.
I took what's known as PChem. I can't remember what the P stands for, but it was just such heavy math. And so what it was every estimation that you used, like it would be like so you'd come up with an answer based off of a measurement that because here's the thing. Like even when you're measuring things out, the measuring tools that you have margins of error. So if you're measuring out, let's say that you're measuring out um, zero point zero 0.05 grams of carbon, you can't just go zero point zero 0.05 grams of carbon. You'd have to go zero point zero 0.05 gram, like zero point zero 0.05 plus or minus 0.0325 grams of carbon. And so you have to take into consideration your margin of error. And every time you have a margin of error, it changes the amount of significant figures you're allowed to put into your calculation because of how sure you are on your calculation.
Uh-huh.
And it just all added up on each other. And I was just like, this makes no bloody sense. And then I was like in my biochem. And so, like, yeah, so freaking biochem is basically it's like, okay, so you've mixed all the ingredients together and now you've got formaldehyde. Congratulations. Measure out your formaldehyde and give us the percent yield. And so like you have to figure out how much you put in, how much formaldehyde you got out, your margins of error, you do your percent yield, like all that kind of crap.
Mhm.
And it was just so exhaustive. Whereas molecular biology was like, okay, now pour this into here, and it turned blue. Congratulations, you got your answer. I like molecular biology better. But
Seriously though.
I highly, highly, highly doubt that this class is going to get that in depth. But
Hopefully.
but yeah, so when you're dealing with when you're dealing with margins of error, it every margin of error compounds upon the next one that you have to deal with, and
Mhm.
adding versus timesing and dividing is a total mess because like adding fractions versus timesing fractions totally different ballparks. Like
Yeah.
that's how margin of error is. If you're adding margin of error, not too bad. If you're timesing or dividing margin of error, no. Just no.
Like, no,
So
gosh, that sounds horrible.
it seriously was. It was the class I took it in the summer
Hmm.
because I was actually really close between either molecular biology or biochem. I was
Hmm.
like maybe one class away from difference between the two. So it was like It was like 12 credits in one and 16 in the other, you know?
Mm-hmm.
So during the summer, I took PChem and then dropped it the first week because I was like, what the crap? And then I was like, okay, well, let's try it again during the fall when it's slower and it's not so fast paced. Took it again,
Yeah.
dropped it, and I was like, okay, screw it. I'm molecular biology.
Ooh.
That class was like, oh my gosh, the math. Like, I'm not a math phobe. I took the both parts of uh calculus, you know. So I took Calc 1 and 2, so I understand calculus and stuff, but like this stuff was just like, oh my gosh, the math just scared me. Like it was
If it scares
awful.
you, then it would like kill me. So I can't even imagine.
So, like
That's
I said,
awesome.
that's a tangent. This class, I know this class isn't going to get that bad. I'm
Mhm.
just giving you a heads up conceptually
Yeah.
that stats in real life isn't this clean.
Yeah.
Usually we have to estimate the sigma based off of other things, and that's how we get our standard deviation. And
Okay.
we'll probably have to estimate sigma at some point,
Hmm.
but I highly doubt we're going to be doing or like basically any mathematical operations with margin of error, you know,
Yeah.
because sister Cook is nice and just says round to three decimal places as opposed to make sure you have the correct significant figures.
You're like, oh gosh.
Uh,
Okay.
yeah,
Thank you,
no,
Mr.
yeah,
Cook.
it'd be like such a pain because you'd get like one measurement that was
Hmm.
super accurate to like seven significant figures, like just
Yeah.
super accurate. And then your next one, based solely because you're using a pipette as opposed to this nice electronic machine, you'd have
Yeah.
like two significant figures. And so you'd have this, and then you're just like, okay, my result, I have this huge, nice figure, and my result's going to be two significant figures. And it's just like, oh, that just ruins everything.
That's crazy. That's tense.
Anyway, so heads up on that. So
Yeah, really though, I can like mentally prepare myself for what's ahead. Oh goodness. All right. So, hmm. Okay, so do we use the applet for question three?
So we don't have to if you have the numbers memorized, do you?
It is, I have them written down. 1.645.
Okay. Because yeah, two standard deviations, 1.96 is the only one that I have memorized right now.
Oh yeah. Yeah, 90 is 1.645. Okay, help me out with this one. So, do we do um 50? Mm. What's the formula we use for this?
So margin of error,
Okay. And so that's um the mean minus the margin of error, and then the sigma over that one, right?
you're totally on the right track, but you're overcomplicating things. This was
Mhm.
actually a question on the homework that I had the exact same thing I had to stop and figure out.
Okay.
So what's that the equation for? When you go sigma, so you go difference between mean and mu
Hmm.
times sigma divided by n squared. What's
Hmm.
that equal to?
That's equal to the confidence interval?
No, we're dealing with the confidence interval right now. So this goes back, like, even
Oh,
before this unit started,
it's
we're
the
dealing with
mu,
this one.
right?
Mm,
Oh, dang it.
so the mu was in the equation. So mean minus mu
Uh-huh.
divided by sigma divided by square root of n. Do you remember
Yes.
what that's equal to?
Uh, Dang it. Okay, I don't know. Tell me.
I'll give you a hint. It has to do with the applet.
Um, s- so like the standard deviation?
And how do we measure standard deviation?
Um, it's given to us. Oh,
On
dang
the
it.
applet. How do we measure standard deviation on the applet? Or I should rather say, how do we measure the number of standard deviations?
Well, we can put the area as 90% or whatever.
Okay. You're getting the units confused.
Okay,
You'll
so
understand the concepts, but okay. So if we okay. So if we take the mean minus the mu, what does that give us?
the mean minus the mu is the variance?
Not yet. It's simply the difference between our observation and the mu, right?
Yeah.
And if we times that by sigma divided by the square root of n, what does it give us?
Z-score?
There you go.
Okay.
And then in this instance, we have got sigma and n. And what is the third variable that they've given us?
They've given us um the confidence interval.
Well, they told us how confident we want to be. So they said make a confidence interval of 90%,
Okay.
which in a roundabout way gives us a third variable in value.
Yeah.
So what do we know about a confidence interval that's equal to 90%?
It's 1 point, it's equal to 1.645.
Exactly. So they're giving us how confident they're giving us how confident our confidence interval is. So either 90%, 95, or 99, which
Hmm.
is basically an indirect way of telling us what our z-score is. Because knowing how confident we are, there's a one-to-one correlation with how confident we are and what our z-score is.
Oh,
So
that's right. Because then I was talking about the asterisk, and when it has the little star thing next to it, it means it's like it's a yeah. Okay, yeah, okay.
yeah.
That makes sense.
So yeah, like they're saying the confidence interval, that would be if you decide, let's make our confidence interval 95%,
Mhm.
just because that's a good standard. And then you calculate how big of a sample size you need in order to get a confidence interval that's not going to be too wide, you know.
Mhm.
That's what that was talking about. Sometimes what happens is you'll do your study and you'll have you already set, you know, alpha at 0.05. But
Mhm.
the thing is, your value is so ridiculously good that you end up getting a confidence interval of like 98%. And so rather than giving your confidence interval, like, yeah, so like you'll get a value that gives you a really good confidence interval, like
Uh-huh.
98%, but
Mhm.
it's not a super wide. So like um, let's say you have an average of 100 And as your confidence interval increases, the margin of error increases. So if your confidence interval is 90, let's say that your margin of error is it'd be smaller, so let's say 95 to 105. So it's basically plus or minus 5,
Okay.
but it's not a linear progression. As you go up and become more confident, it doesn't necessarily just go, oh, let's jump up the same amount of units. So if a confidence interval of 90% is plus or minus 5, a confidence interval of 95 could be, depending on stats, the thing is, it could be anywhere between plus or minus 6. So, like, it's still really close. And you're just like, well, let's just go with the 95% confidence interval because we're more confident with it. On the other
Mm-hmm.
hand, it may be due to calculations, it may be something like plus or minus 50. In which case you'd be like, okay, we're less confident with a 90% confident interval. But the thing is, it gives us a nice tighter edge. And we're just saying the average is going to be between 95 and 105, as opposed to saying we are 95% confident that the average is between 50 and 150, because
Mm-hmm.
that stat's useless.
Yeah.
So sometimes what will happen is that you get an awesome confidence interval where it's even higher than the standard 95, but it's
Mm-hmm.
still a really small range. And that's when you don't have a Z star. So the Z star is basically saying we're deciding beforehand this is the confidence interval we want, so calculate based on this confidence interval. So that's what that little Z star meant.
Okay.
So unless you start getting into like experiments and studies and stuff, you're not going to see it. But I saw that in the text and I was like, that wasn't very well explained. So
Yeah.
so just a heads up on that. But for this class, I don't think it's going to make a difference. Like I think it's just Z score is Z score. So don't worry if there's a star or not.
Okay. Okay. So the confidence level is giving us the Z score.
Yes.
Okay.
So we have three values. They may ask something rando, like a 93% confidence interval, in which case you'd have to run to the applet.
Yeah.
But for the most part, 99% of the time, we're going to see a 90% confidence interval, 95 or 99. And those numbers are 1.645, 1.96, and I think 2.574. I'm not sure about the third one. I'd have to double check. But 99% of the time, we're going to be using one of those three numbers for our Z score.
Okay.
Okay, so can you solve it now?
So do I just plug it into um Z score times sigma plus mu equals X? Or is that not right?
Are they asking for an X?
Mm,
Or I should say, are they asking for a mean?
no. Find the margin of error for.
And you said plus mu, have they given us a mu?
No, they have not.
Yes, so they are not asking for that. They're asking for basically, how it would show the mean plus or minus a value.
Mm-hmm.
That plus or minus is the margin of error. So they're asking, we're not giving you the mean yet, so don't worry about that. Just figure out what the plus or minus value is at this point.
Oh, okay. Wait, that is so that is that the same thing as the 1.645?
Say that again.
Huh. I need it. But so the Z score is different than the margin of error. Or is it the same thing?
It is different.
Okay.
What's the difference?
The difference is I can never find my pencil. um
And this is actually a really good concept to understand. So what's the difference between the z-score and the margin of error?
Uh, man, was I sleeping when I read through this or what? Uh, okay. It just talks, what the heck? So it talks a lot about the 68, 95, 99 rule. Um, hmm. Hmm. I guess so. In the example it gave you, it was like the common value for the margin of error in political polls is 3%. But like, how did they get 3%?
So here's a question. What does the z-score measure?
Z-score measures how big the standard deviations are.
Yes. Do you have the applet open?
Yes.
Okay. So go to the applet
Mm-hmm.
and highlight the center section and then type in a z-score and any old z-score.
Okay.
Okay. So the area is highlighted and looking above the curve, what information do we get from that z-score?
The area.
And what's the area?
Um, the area um, is also.
Okay, let me put it this way. What are the units of the area?
Oh, you've totally told me this before. My brain's like not on tonight or something. It's like not.
You're coming off of a holiday, don't worry.
um. Hmm. Uh. I mean.
Trick question. The area under the curve does not have units. It is
Okay.
probability.
Okay.
So what we have highlighted and the area is saying, so for example, if we type in a z-score of 1 and
Mhm.
it says area is 0.6827,
Mhm.
that is telling us that there's no units there. Basically, it's saying of all the data that we have, 68.27% of that data is condensed between those two z-scores, the negative and the positive.
Yeah.
That ringing a bell?
Yes.
Okay. What we're doing with margin of error is we are finally applying units to that z-score we're given. So
Okay.
for so for this question, it is saying, oh, they didn't put units on it, the jerks. Okay.
Mhm.
Let's say that this is 95% confidence interval. And let's say this is a sigma 50. What would be a sigma 50? Let's say this is MCAT scores. So MCAT scores have a unit, basically correct out of total amount of questions, right?
Mhm.
Well, that gets ugly when you go plus or minus. Let's change this. Okay, let's say instead this is elephants with a sigma of 50 kilograms. Standard deviation of the entire population of elephants is 50 kilograms, and they just spread out like that, you know?
Mm-hmm.
And then they give us the sample size, and that sample size is what we need in order to determine our standard deviation based from sigma. And so what we're doing is we're finally taking that 90%, which is unitless, and applying the units of kilograms. So rather than saying that all elephants, like we have this curve and 90% of our data is here, what we're going to be saying is that we are 90% confident that the average for all elephants is going to be whatever kilograms. Does that make sense?
Yeah.
Okay. Because this lesson gets a little weird because it jumps from um, like probability, kind of the way that we're used to, but then it talks about the way probability really exists. Because what's happening is, did you read the section about flipping a coin?
Yeah.
So if I have a coin and I haven't flipped it, what's the probability that it'll come up tails?
Um, the probability, they worded it weird. So like the probability that it will come up, it was between like 0 and 1, but the probability of getting heads is 0.5, so 50%.
No, this is where it gets tricky.
Okay.
So the probability before I flip the coin is 50-50. So
Okay.
50% chance that it's heads, 50% chance that it's tails. If I flip that coin and cover it up and we haven't looked at it, what's the
Then
probability that it's tails?
0 or 1.
Exactly. It either is or it isn't. There isn't any in between. So just
Yeah.
because we haven't seen it yet doesn't mean that the probability hasn't been determined.
Okay.
And so that's what we're doing with these confidence intervals is we're setting up an interval of a minimum to a maximum. And what we're saying is that um, the odds, so the probability that mu is within that confidence interval is 0 or 1 because mu is already set, it's either in there or it's not.
Mm-hmm.
But what we're doing is we're creating an interval where we are saying we are 90, 95, or 99% confident that it's in there. The fact is, it either is or it isn't, but we are 95% confident that it is because if we were to do this study over and over and over and over and over again, so again, possibilities that haven't occurred yet, if we're to do the study over and over and over and over again, 95 out of 100 studies would have the mu within their margin of error. So does that make sense?
Yeah.
Because yeah, probability is yes or no. Is the mu within this in the margin of error? Well, it's either yes or no, and we don't know until we know the mu. And once we find the mu, we can see, okay, was it within, or were we wrong and it's 0? The probability is that. But the thing is, if we have multiple studies that we can execute in exactly the same way, so a sample size of 25, again with simple random samples, making sure that we're unbiased in the way that we select them,
Mm-hmm.
those things haven't occurred yet. So there's probabilities that can still occur with that. And so basically there's a 95% chance that our next study will have the mean within our margin of error. But then as soon as we do that study, it then goes to 1 and 0. But then the next study is, again, there's a 95% chance that it's in there. And then once it's done, it's either 1 or 0. So what we do is we conglomerate all of them and say that if we do this study over and over and over and over again, 95% of them will have the mean within their margin of error. And that's what it means by confidence.
Okay.
So it's really nitpicky between the probability of saying there's a 95% chance that the mean is within our margin of error
Mm-hmm.
versus we are 95% confidence. You know, to the layman, they mean exactly the same thing, but there's a very special distinction between that because the fact is once your study is complete and the mu already exists, the probability is either 0 or 1. So it doesn't make sense to word it that way.
Okay.
So does that make sense? You got kind of a confused look on your face.
It makes sense.
Okay,
It
let me
it
let me let me pose this to you because this is a problem that has come up.
hmm
People still don't know the answer to it, but it's really weird. Have you ever heard of the Monty Hall problem?
No.
Okay. Um, have you heard of an old? This is before. This was basically, um, what's it called? This was uh, the Price is Right before the Price is Right. Have you heard of Let's Make a Deal?
Sounds familiar.
So, like I said, it was the Price is Right before the Price is Right. So it was back in the '60s.
hmm
The host of that show was Monty Hall. What he would do is at least one point in every episode, he would present someone in the audience with three doors. And what would happen is they would have to choose a door, and behind two of the doors were just non prizes. So, like a donkey or a flat tire. And then one of the doors had an actual prize, like a vacation or a car or just money, that kind of stuff. So
hmm
that's the way it worked. So, what they would do is the person, and they only had, so before ever choosing, when they're making their decision, what is the odds that the person will win the prize?
1/3.
Okay. This is how they threw a wrench into it. And people are still debating about this today.
hmm
What happened was after you'd chosen the door, then Monty Hall would open up one of the other two doors and show a non prize. Because
hmm
obviously he wouldn't want to open the door to show the prize because then you would just switch over to that. So he opens one of the doors and lets you choose again. And now you know one of the doors that doesn't have the prize in it. But the thing is, when you're first choosing, you had a 1/3 chance. So there's people saying that okay, when you first started, you had a 1 in 3 chance. And that's just how it was. And then
hmm
when one of the doors opened, that doesn't change stats. Probability hasn't changed. You still have a 1 in 3 chance of being correct. And if you switch, you'll still have a 1 in 3 chance of being correct. And so there's no point in switching. There's another group of people who say, okay, opening the door has actually changed the dynamic of it
hmm
because the door isn't opened at random. It is specifically a door that A, you didn't choose, and B, doesn't contain the prize. So basically, it resets it to a 1 in 2 chance of winning the prize. So
Yeah.
your original choice was 1 in 3. So you always want to choose the third door because now you have a 50% chance of winning it.
Hmm.
And that's something that's still being debated today because of the way probability works and how chances it's either yes or no. But just because we have a flare of unknown in there, people tend to think, well, there's a 30% chance, there's a 33% chance that the car is behind this door. No, there's a 1 or 0%, there's a 1 or 0 that it's behind that door. It's just that you don't know.
hmm
So did that clear up a little bit or did that just confuse things even more?
No, it makes sense. It makes sense.
You sure?
Yeah. Um, yeah, it makes sense.
Okay. I'm going to quiz you on this on Thursday. See if it does make sense. Because it's
Oh,
it's very it's very semantic. It's
uh-huh.
very semantic, but the thing is it's also very very important.
Mhm.
Um I remember I taught a Sunday school class in Texas. I was a Sunday school teacher for the high schoolers. It was like the best calling ever. I loved it.
Yeah.
Um, but we had a lesson, and I was trying to instill this. We didn't get into the math part of it, but it was very important that you choose your words correctly, and that's what they're doing here with stats, even if you don't understand it.
Mm-hmm.
And the example that I gave is I wrote up on the whiteboard, and this was like before giving them any input. I just wrote up on the whiteboard. I wrote, "This snake is very poisonous." And then I stopped for a second and erased the last word and replaced it with venomous. And then we had a discussion about that.
Hmm.
And basically, what it came down to was that even if you don't understand it at your level, the thing is, there's a level where those little changes are very important.
Mm-hmm.
Because to my class, hearing, a bunch of high schoolers, that snake is poisonous, that snake is venomous, both of those groups are going to be, oh, okay, that's a dangerous snake, let's just ignore it. But let's say you're a wilderness survivor, and the difference between venomous and poisonous, you know the differences?
Is venom like with actual animals, but poisonous is with like plants and stuff?
Poison only affects you if you ingest it.
Oh, I
So
did
if you
hear that.
so
Okay.
if you
Yeah.
ingest poison, then you're in trouble.
Mm-hmm.
If it's venomous though, then the snake can get the venom in you without you eating it.
Yeah.
So it's a huge difference for a wilderness survivor, because if they see this snake is poisonous, they have to stop. Oh crap. Did they mean poisonous or venomous? Because either way, I'm not going to eat it.
Mm-hmm.
But does that mean that I have to be chase it off or kill it? Or if it bites me, I'm just going to get a rash and that's it. Or if it bites me, it's going to kill me. Like that's a huge distinction
Mm-hmm.
once you go up a level above the layman.
Yeah.
And that's what they're doing here with confidence interval, level of confidence, and probability. Is that
Okay.
to the layman, it all sounds the same. There's a 95% chance that the mu is going to be between our margin of error.
Mm-hmm.
And a statistician would be like, no, no, that's completely wrong. We are 95% confident that the mu is within our margin of error. So to the layman, they're exactly the same. Once you go up a few levels, it's wrong. And that's why they're writing it out like that in this text.
Okay.
So honestly, you can just kind of think of it that a confidence interval to 95% is that the mu will be in there 95% of the time.
Mm-hmm.
So if we do go up to the next level, we can have a discussion on that. But that's why the text just went so deep into this is why it's not probability, and this is why we say we are confident rather than there's a 95% chance that it's there.
Yeah.
So does that make sense?
Yes. That
Okay.
makes sense.
Okay. If it gets more important, then we'll dive into it again.
Okay.
But like I said, for the layman, they're interchangeable. Venomous, poisonous, they're interchangeable for the layman,
Mm-hmm.
Once you go up a few levels, those things make a huge amount of difference. Um, so if we do go up those levels, then we'll just chat about this again. Okay.
Okay.
Okay. So margin of error, how do we calculate? Oh, yes. What we're talking about, margin of error is finally putting units onto our z score. So the z score and the area are unitless. And so here they don't give us any units. They'll probably give us units later down the line. But basically, what we are doing with our margin of error is we are taking those unitless numbers
Mm-hmm.
and adding units to them to
Okay.
actually make them more applicable.
Okay.
So, like I said, uh, standard deviation of 50, that doesn't really help. 90%, which is going to be a z score of 1.654, those are all unitless. The whole point of a margin of error is adding units to those unitless numbers.
Okay.
So, do you remember the equation?
I guess that's what I am confused about. Which equation do we use? Do we use the mm, oh, because the equation that I saw in the text had mean in it. If we don't have the mean, then
So that's part of the confidence interval.
mhm.
There's two parts to a confidence interval. Do you know what the two parts are?
Um, no.
Okay.
The plus and minus.
Yeah, that divides two parts. So do you know what the two parts are?
Well, so it talks about like the standard deviation. If it's two standard deviations away, then you put a 2 in front of the sigma divided by n squared.
Yeah, and so what we're looking at is so we have a number plus or minus another number. That first number is going to be our mean.
Hmm.
The plus or minus is then the margin of error. You put the two together and you get a confidence interval. So you do need a mean in order to do a confidence interval.
Hmm.
Here they're only asking for the margin of error.
Okay. Um, um, so what is the difference between the z-score that you get, which is, for this case, it would be 1.645 in the margin of error? I guess, how do you get the margin of error?
The z-score goes into the margin of error. It's a new equation that they gave us that we just have to memorize.
Okay. Which is which is 2 um sigma over n squared, right?
When would it be 2 sigma?
When it's when you're 95%.
When close, when your z-score is 2.
Okay.
And what did this lesson kind of hammer into your head? That we've been using a z-score of 2 to estimate 95%, but the
Hmm.
real 95% z-score is 1.96.
Yeah, so we would
So
use
we
so we instead of that same formula, except for we would use 1 um 645, right?
1.90%, 1.645, yes.
Okay.
But I also heard, here's Freya. Freya?
Oh.
Her, her daddy is house sitting, so he's been gone for a week, and she's become really needy without him. Can you say hi?
Oh.
Can you say hi?
Hi.
Aw.
Yes, where's my cat? I need some loves for my cat. um,
Okay, so what's the equation one more time?
okay, so it's the z-score,
Mm-hmm.
whatever it is, in front of sigma over n, the square root of n.
Yes. Last time you said n squared.
Oh yeah, my
So
bad.
that would give you a super tiny number. So you totally caught yourself there. Okay.
Let's see. Mm. Okay. Okay, I think I typed this into my calculator wrong.
What'd you get?
But did you get 411?
Okay.
I think this is just
So sigma is 50 divided by, well, sigma, so 50 times less than 2 divided by 5. Is that going to be coming to a number bigger or smaller than 100?
yeah. How do I type like the coefficient like a big 2? Do I just do not a big 2, I guess the 1 point
1.645.
yeah,
Are you on a calculator or are you using Excel?
calculator. um I I'm gonna try Excel. Okay, I don't know what I'm doing. What the heck? Uh
I'm going to screen share real quick. Okay. Are you seeing my screen?
yeah.
Okay. So whenever I'm working, this is what I was doing when I was working on the homework earlier. So got variables here, mu, mean, sigma, n, z, and margin of error. Over here, z-scores of 1, 2, and 3. And then before I had the equations written out. So if we want m is equal to sigma times our z-score divided by the square root of n. This is a reminder. And then if we're looking for the number of samples that we have to, like the number of people we need to get a certain margin of error, then it's just pretty much the same thing. Sigma times z-score divided by the m, and then square all of that. So this is what I was just working on when I had the homework. That way I had basically all the information that I needed. So margin of error, as we have right here, is going to be equal to sigma, this one up here, times our z-score right there, which is also incorrect, and then divide that by that. So that should actually be 1.645. There we go. So the margin of error should be 16.45.
Okay. Let me try this one more time. So sigma.
So is Excel working for you, or is just a calculator just easier for you?
I just, I really should use Excel, but I'm just so like old school, I guess. um, Let me try one more time on my calculator. Can you screen share your Excel one more time?
Yeah. Okay. So we aren't given a mu or an average. We just have sigma n, and then obviously the square root of n is just the square root of n, and our z-score. And so the equation that we're using, b3 sigma times b6, our z-score, divided by b5, the square root of n.
I just took a screenshot. Okay, so times z-score of okay, I got 16.45.
Okay, perfect.
Ugh. Oh, sweet mercy.
Okay, what does that 16.45 represent?
So that represents the margin of error. So you would plus or minus that from your mean.
Okay, perfect. Okay, so you understand the two parts of it. You have the mean, and then you have your margin of error,
Yes.
which actually leads into the next question. They name it something different, but do you know the answer to question 4?
So which of the following statements is true? Do, 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 do. Oh, this would be so this would be the mean is a point estimator of the mu.
Perfect.
Okay.
So mean is the point estimator that we use when we're dealing with confidence intervals. What's the interval estimator?
The interval estimator is I have right here, the range of plausible values of a parameter, so a population. So that's kind of where the margin of error is. It's the
Exactly.
adding or subtracting of the margin of error.
Yes. So if this was, rather than just choose one right answer, if it is one of those squares and you just click all the correct ones,
Mm-hmm.
and it said M or margin of error is an interval estimator, then you would click that one also.
Okay.
So it sounds like you understand point estimator and interval estimator and
Yes.
what the two parts are and how they combine to make one confidence interval. So that's good.
Okay.
Okay. And next question, we finally have some units. Okay.
Um, okay, so what is the point estimate?
So when it comes to confidence intervals, what is our point estimate? There's a point estimate and an interval estimate. So what's the point estimate?
Uh, the, mm, the
Roll
point.
up to question 4 if you need to.
So the point estimate is pretty much the mean, standard deviation, and variance. And then the interval estimator is the margin of error.
You have the definition right, but then you confused a few things. Because the standard deviation, z-score, and the n are going to be included with the margin of error, whereas the point estimate is simply the mu.
Oh.
Because yeah, the mean is just a point, just a single solitary point. And then you take the rest of it, z times sigma divided by n, the square root of n, and
Mhm.
that gives you the plus or minus. And that plus or minus is then going to be the interval, whereas mean is just a single point in that interval.
Okay.
So what would be the point estimate for number 5?
Um, the mu?
Are we given a mu?
No, so we have to calculate it.
Not yet.
Um,
What does the answer to question 4 state?
oh, is it the same as the mean?
Yes,
Oh
because
gosh,
it's asking what is the point estimate.
uh-huh.
Mean is the point estimator for mu. So it's not asking, we're not asking what mu is yet. We're just asking what's the estimate that we're using to hopefully narrow down mu. And that would be our mean.
Okay. Gotcha. Okay. Whew. Is the margin of error? So would this be 27.685?
That's what I got.
Okay.
And question 7 or 8 are basically the plus minus aspect of the confidence interval.
Yes. So so would it be 498.315?
Mm-hmm.
Okay. And then 8 would be 553.685.
That's what I got. Okay, so putting this all together before we move on to question 9, what does this mean conceptually?
Conceptually.
Yes.
um,
Like if these were the results that you got in your study,
mhm.
you had to report your results, your findings to the school or whoever you're researching for. How would you present this? What would your conclusion be?
So we would say that we are 95% confident that our scores would be between um 498.315 and 553.685.
Okay, perfect, except for one thing.
Okay.
You said our scores are between those two numbers.
Mm-hmm.
And you're actually totally right to say 95% confident as opposed to there's a 95% chance.
Mm-hmm.
That's how you'd want to phrase it, is we are 95% confident.
Mm-hmm.
What's the score?
The score is 526.
Well, that's the sample mean that we got. And since
Um,
that's our sample, we're 100% certain that that's our sample mean
okay.
because that's simply just adding up all the scores and dividing by 64.
Okay.
So we're extrapolating here, and what are we extrapolating to?
That our margin of error is 27.
We know what our margin of error is. We've calculated that out.
Okay.
So that's a given.
Mm,
So what's the first sentence in the question?
for
Uh,
number nine.
for above, well, actually, okay. So before question 5, they give us that paragraph full of information. What's the
Yeah.
first sentence in that paragraph?
Gina wants to construct a 95% confidence interval for the GMAT scores.
Yes. So what are we 95% confident that?
Um, we're 95% confident.
Are we 95% confident? Because I said that wrong too. What would you say? Actually, no, you're right. 95%. The percent threw me off. Yes, we are 95% confident. We have a confidence of 95%. Either one. Just don't say the probability. Just leave
Okay.
probability out of
Just
there.
don't use probability. So we're 95% confident that
What are we 95% confident of?
our score, these scores,
What scores?
the GMAT
What
scores,
about the GMAT scores?
will um
So are you saying that you are 95% confident that all GMAT scores fall between 498 and 553? So
yes.
you're saying that everyone who has taken the GMAT, even though that there's a standard deviation of 113, well, there's a sigma of 113, that we have a sigma of 113, but we are 95% sure that everybody who takes the test is going to score between 498 and 553, which is only plus or minus what, 30, 40 points, even though we have a sigma of over 100.
So the standard deviation is talking about the actual within 68% of students will be within one standard deviation, which is 113, which is a really big standard deviation, but we're 95% confident that our um, Oh, huh? I thought I got it, and then it like didn't click.
Okay,
So like
let me
the
put it this way, see if this makes sense. Okay, the GMAT's done on computers, right?
yeah.
So basically, well, if it's not done on computers, it's scored with computers, you know? So that means even if millions of students are taking the GMAT every single year, with
Uh-huh.
computers, we can get an exact average. We know exactly what mu is. We know what the population mu is, right?
Mhm.
So if you're working for the state, if you're a government worker with the GMAT, you already know what mu is, right? So there's no this entire thing is worthless because you can just pull up the data. This is what mu is. We
Yeah.
have Gina though. Let's say Gina doesn't work for the state. Let's say that she is just a BYU student who's just curious about the GMAT. And she can't go digging into those files to discover what the average GMAT score is. So instead, what she does is she somehow, I don't know, through hacking and some super elite cyber friend, discovers that sigma is equal to 113. We're just going to hand wave that. She just knows it. Okay. So she knows the sigma, and
Uh-huh.
she's like, okay, I figured out the sigma. Let's get a large population size, and I'll just ask students around campus, and from their responses, I'll use that to estimate what the entire nation's average for the GMAT score is. So
Mhm.
then she gets her sample mean, X. Her sample mean is X. She already has sigma and she knows how many people she asked. So
Mhm.
she plugs in her numbers and gets a margin of error. And when she plugs that margin of error into her sample mean, she gets 498 and 553. So what is she saying with those two numbers?
She's saying that her mean will be off with a margin of error of 27.
Wait,
Like
say that again. It sounds like you're really close.
she's saying that her mean will be off by 20, a margin of error of 27.
And what does that mean?
That means
Her
uh,
mean is off of what?
um, I guess you could say skewed. Not skewed. That's a bad word. You could. Mm. uh, like
We're
there's.
so close.
I don't know. um, that you can plus or from your mean, you can plus or minus 27.
What happens if you plus or minus 27 from her mean of 526?
That that's your um confidence interval.
And
No,
what are you confident about your confidence interval?
that it's 95%.
What are you 95% confident about your confidence interval?
That it's 27.
Oh no, you already know that it's 27. You calculated that out. What are you confident 95% confident about your confident interval? Because she's 100% confident that her mean is 526. She's
Mhm.
100% confident that n equals 64. She's
Mhm.
100% confident that her margin of error is 27. So her 95% confidence interval, what is she saying she's 95% confident of?
The margin of error,
Mm,
her results, her um
her results, elaborate on that. Her results as it pertains to what, or her results as it compares to what? What is she 95% confident that her results are what?
She's 95% confident that her results are true.
True as in terms of what?
Um,
What's the variable that we don't know?
we don't know the we don't know. I mean, like, we don't actually know the GMAT scores.
We don't know the average for the GMAT scores, yeah.
Yeah.
And since she doesn't work for the state, she doesn't have access to the GMAT score, so she doesn't know what the true average of the mu is.
Mm-hmm.
So she is saying, I interviewed 64 people, and
Mm-hmm.
because I interviewed that many people, I am 95% confident that the population mu, so the mean for the entire population of the United States, falls between 498 and 553, which means that my mean of 526, I am confident that my mean of 526, I am 95% confident that my mean of 526 is no more than 27 away from the actual mu.
Oh, okay.
So you had it, you just kept going around in circles, and then every pass you'd go a little bit farther away to let you
Okay.
know you had it. So does
Okay.
that make sense?
Yes.
So that's what she's saying. She's saying, I don't know what the GMAT scores are. I don't know what the average GMAT score is for the population because I don't work for the state. I don't have that kind of access. But the thing is, my friend uh, who works in BYU acceptance knows the sigma, and he told me what the sigma is, so I have the sigma at least. And using that sigma, I'll just interview some people around campus, and I can estimate what the
So
average
we're
would be.
always going to be comparing like the sample mean to the population.
Yes. Yeah, and like I said,
That's
this is
kind of this whole thing. Like we're comparing a sample to the actual population.
yeah. Yeah, this isn't the best example because the fact is, like I said, GMAT is scored by computers.
Yeah.
We know what the mu is for the GMAT scores. The computer will
Mm-hmm.
just pop that out for us. Let's say instead that this was she wanted to make a 95% confidence interval for the mu of population height in America. That's not something we'd know. That means you'd have to go to over 300 million people in America and
Mm-hmm.
measure their height and then average it out. And that's not going to happen. There's just simply no way of doing that.
Mm-hmm.
So in that case, we would sample a few people, like N64 or how many people we'd interview, and
Mm-hmm.
then we'd come up with a confidence interval and say we are 95% confident that the average person in America are between these two heights.
Okay.
So this wasn't the best example because yeah, GMAT score, we know what the GMAT scores are. We
Yeah.
use confidence intervals when it's things that there's no way you could know you could know the numbers for everything. Like
Yeah.
the let's say body temperature of the average mountain goat. Well, first off, you'd have to gather every single mountain goat in the world and take their temperature when they're not sick. Like it's not feasible. You
Yeah.
just make an estimate. So that's
Yeah.
what we're doing here. Exactly what you said is we're taking what we do know and using that to make a reasonable estimate about the entire population that we can't possibly know.
Okay, so the correct way to always phrase it is, I mean, we're pretty much just comparing our sample mean to the population. So we'll say we're 95% confident that our our mean is 27.685 away from the mu.
Within 27.685.
Oh, yeah. Okay. Yeah.
Because yeah, so
Within.
it's
Because
either 27 or less. Yeah, that's one
okay.
way to do it. The other way to do it is with the interval.
Hmm.
So in that case, you would say we are 95% confident that the mu, so the population mean for the GMAT scores, fall between 498 and 553. They both mean the same thing. It's two different ways to report your data. So
Okay.
make sure you understand them because Sister Cook's going to be asking you to report data in both ways.
Okay. So even though we don't know the mu, we can still say that
We can make
the
a good
mu.
estimated guess.
Okay. The mu. Okay. That makes sense. Okay. I get
And
it.
like and like I said, the probability spiel that we went on before,
Hmm.
in this case, we wouldn't say that there's a 95% chance that the mu falls within these two numbers
Hmm.
because the chance of it happening is either 0 or 1. We have our range and then there's the mu. And the mu either falls within the range or it falls outside of the range. It's either 0 or 1.
Yeah.
But what we're saying when we're saying we are 95% confident, we're saying that if we did this study, if we did this exactly the same, so we used this sigma, we used 64 people, and we made sure that the people were chosen randomly
Hmm.
without any bias. If we did that an infinite amount of times, mu would be inside of our interval 95% of the time.
Yes.
So if you did it an infinite amount of times.
Hmm.
But the fact is, we can't do it an infinite amount of times, so we just change the language to say we are 95% confident that it's in there.
Okay. Yes, I get it. It
Okay.
finally connected. Okay.
Well,
Mm,
this is different than what we've been doing for the last little while. The last little while is we've been looking at individuals and seeing where they fall as outliers on
yeah.
a distribution curve. This one, we're now taking it a step further and
Mhm.
estimating true values based on the information that we're given. So we're
Yeah.
doing so it takes a little bit of a mind twist.
Yeah, it's yeah.
Okay. So does that make sense? Move on to question 9.
Yeah.
Okay. So what happens to the width of the confidence interval if Gina increases the sample size?
There would be no change.
Why do you say that?
Um,
So what are the two parts of the confidence interval?
uh, standard deviation.
No, not yet. There's
Oh,
two big components that we can then break down even more. So what are the two big components? They are vocabulary words that we learned just for this lesson.
um, are you talking about like point estimate,
Exactly. Point estimate. What's the other one?
interval estimator?
Okay, so let's look at this. If she were to change the sample size, if Gina increased the sample size, would that affect the point estimator?
Um,
What's the point estimator?
is the mu.
Is it the mu? Mu is what we're trying to estimate.
The point estimator is, wait, it's all of them, right? The mean, standard deviation, and variance.
No, if we did all of that, then that becomes the confidence interval.
Oh,
So the point estimator of the confidence interval, so the point estimator is simply our average, our sample mean. So I think that
okay,
was
wait, you broke up just for a second there. So the point estimator is,
the point estimator is our sample mean. So what question 4 says. Our point, so means mean, our sample mean is the point estimator for mu. And so we have that estimator, and then we
Uh-huh.
throw the margin of error around it to hopefully catch it if we're wrong. So the
Okay.
point estimator is just simply mean.
Okay.
And the mean's not going to matter how big or small the population is, right?
Correct.
Okay. So what's the second point after the point estimator?
The interval estimator.
Okay, so the interval estimator, what's that equal to?
The margin of error.
And what's the margin of error? What's the equation for margin of error?
Um, so it's gonna be whatever percentage, and then standard deviation over, or sorry, sigma over um square root of n.
Okay, so we're dividing by the population, by the sample size.
Yes.
So if as n gets bigger, what happens to the margin of error?
Oh, oh, it does change it.
Yeah, so our margin of error gets smaller. Our our point estimator remains the same, but our
Hmm.
margin of error becomes smaller, which means it gets closer and closer to our point estimator, making the entire confidence interval smaller.
Okay.
Does that make sense?
Yes, so it will decrease.
So here's a question. Having a smaller confidence interval, is that a good or bad thing?
It's a good thing.
And why is that?
Oh, wait. A smaller yeah, because that means you're closer to the mean.
Exactly. The furthest we can be off is less than if we had a large confidence interval.
Yes.
So, yeah, so having a confidence interval saying the average height, the height of the average person in America is between 6'2" and 6'8".
Hmm.
That's a lot more useful than saying the height of the average American is between 2 feet and 8 feet. You know,
Yeah.
being able to narrow that confidence interval is a good thing.
Is a great, yeah, okay. That makes sense.
So in the last one, we liked large Z's, we liked large Z's because the further something was away from the mean, the more we could be like, oh, P is less than alpha. This makes it a legitimate statistic. So
Hmm.
we liked being away from the mean. In this case, it's just the opposite. In this case, we like being closer to the mean because then we can say, oh, our confidence interval is more likely to be, our confidence interval is more accurate. So rather than giving out a worthless stat that uh, the average income for a male in America is between 0 and 1 million, that's completely worthless.
Yeah.
Whereas if you say it's between 45,000 and 65,000, that's a lot more useful information.
Yes.
So you're totally right. Sounds like you understand. Smaller confidence interval is better. We like smaller confidence intervals because it means we can be more accurate in our findings. Especially going back to PCAM, let's say you use a study. If you use a study in your own study and you have to figure out their confidence interval, the
Mhm.
smaller their confidence interval, the less variables you have to worry about, and the more you can be sure that you're going right, moving ahead. So you're
Yeah.
totally right with that.
So larger sample size will decrease the confidence interval.
Yes.
Okay.
Question 10. What happens to the width of the confidence interval if it's changed to a 99% confidence interval?
Um, so you would divide it by so it would
So which part is this affecting? So on our confidence interval, we have the point estimator and the interval estimator. Which side are we dealing with?
Interval.
Okay, so we got the interval estimator. What are the three components of our interval estimator?
The um, margin of error.
Margin of error is the interval estimator. So what's the three parts that we're dealing with margin of error? There's
Uh,
three different variables.
the sigma,
Okay.
the n,
Okay.
and like the actual, like if it's 90, 95, 99,
And how do we represent that in the equation?
with either, so 99 would be 2.576.
And what does that number represent?
That represents the z-score.
Yes, the z-score. So we have z-score, sigma, and n. So if we're changing our confidence, our level of confidence up to 99, what
Mhm.
number are we changing?
The z-score.
K. And so a
So,
larger confidence means a larger z-score, right?
yes, which
Are we
would,
dividing or dividing by z?
we are, we are, what was the formula? Oh, wait. Oh, okay, so we're dividing.
By the z-score?
So we're doing sigma times z-score divided
Yes.
by the rest.
Yes. So as our z-score increases, what's going to happen to the margin of error?
Um, okay, I think it's increase.
Why?
Because the width of the confidence, so that will increase the z-score, which will increase the width of the confidence interval. Hmm.
You're totally right. Think about it just with some simple numbers. Let's say our sigma and our n is equal to 1. So 1 over 1, that's 1. So
Okay.
basically, we just have z-score times 1.
Okay.
If our z-score is 0.1, then what's our margin of error?
If our z-score is 1?
If our z-score is 1, what's our margin of error? It'd just be 1 times 1 divided by 1.
Oh, okay. So 1?
Yeah. So let's increase the z-score. So if we increase the z-score to 100, what does our margin of error become?
Yeah. So we would do 100.
Times 1 divided by 1.
Yes. So it'd be 100.
So it would be bigger. So as our z-score increases, our confidence interval increases.
Yes.
Okay. Does that make sense?
My brain, my brain, my brain.
Let's do a conceptual example because that math didn't seem to agree with you.
I don't know what it is today. I just like I'm half asleep, I guess. I don't know.
Okay, think about it this way. Um, if you're going to be 100% confident you're to have a 100% confidence interval,
Mm-hmm.
that would mean one of two things. Can you think of what they would be?
Well, my Z-score would be higher, and um, I mean, like, would you even have a margin of error if you're 100% confident?
Yes and no. It depends on the two things. If you're 100% confident,
Hmm.
that means either one, so you already know mu, you're 100% confident, and your confidence interval is one number. It's not even an interval.
Yeah.
The other way, if you don't know mu, but
Hmm.
you want to be 100% confident, what is the only way you can take just some random number, stick it in an interval, and be 100% confident that that number falls within that interval?
Oh,
It has to include all real numbers, negative and positive. So
okay.
a 100% confidence interval would essentially be negative infinity to positive infinity.
Okay.
So a 100% confidence interval is all numbers. It's infinite, stretching back and forth. As you become less and less confident, then that interval is going to shrink. And so the difference between being 95% confident, you can be pretty confident with a 95% confidence, and you're going to have you can get a pretty small confidence interval.
Hmm.
99 is going to stretch that out a little bit. To get that last 1%, you're going to include every number on the spectrum just to get that last 1%,
Okay.
which is why we usually stick with 95.
Okay.
Does that make sense?
What would happen if the width of the cone? Yeah. Yeah. So because the confidence interval went up to 95, it increased the width of the confidence interval because you're including more numbers.
Mm-hmm. Perfect.
Get that. Okay.
Because, yeah, it's like if I asked you, what number am I thinking of?
Ooh, I would say, is it between 1 and 50?
Exactly. And if I was thinking of 13, so you're totally right. It was within 1 and 50, is between 1 and 50.
Yeah.
If you wanted to be completely, if you wanted to be completely 100% confident that you were right, you would
Uh-huh.
say you're thinking of a number between negative infinity and positive infinity.
Ooh.
And you would get it right every single time.
Yeah.
So that's how you can kind of think of a 100% confidence interval.
Okay.
Is it just includes every number.
I like that.
Okay. And yeah, the wider you make your confidence interval, the more confident you are because you're just spreading things out, but it
Yeah.
gives you less useful data, you know.
Yeah. Okay. Hmm.
Okay, question 11.
Huh. Everything in the pencil. Okay, so if we don't, oh wait, we do have these. Never mind. Sorry, never mind.
So what's the three pieces of information that they've given us?
So they've given us the standard deviation, the confidence interval,
Which equates
and
to
the
what?
mark.
So
Huh?
the so 95% confidence equates to what?
1.96.
Yeah, so that gives us our z-score.
So would we do four?
And then what's the third thing that they're giving us?
They give us the margin of error.
Okay, and what are they asking us to solve?
For n.
Okay, do we have enough information for that?
Yes.
Okay.
So do we do 400 times 1.96 plus 50?
Not quite.
Are my order of operations mixed up?
Probably. Let me screen cap with you real quick so you can see. Oops. Okay. So we've got our sigma, our we're trying to solve n, and that's not the correct number. That's just a holdover from the last thing. We got sigma, our z-score, and then our margin of error. And then I threw the low end and the high end when they ask for that, which is just simply x plus and minus m. But since x is 0, you can see that it's just equal to plus or minus m.
Mm-hmm.
Anyway, so our margin of error is equal to sigma times z divided by the square root of n. So if we're to switch that around and solve for n, the very first thing we would do is times both sides by the square root of n, which would give us square root of square root of n times m. Uh, Doing the actual steps is annoying on Excel. That's the equation right there. It's sigma times e divided by m to the second power. Does that make sense going from this to this? Do you want to
Yeah.
walk through that, or do
Let
you
me
know algebra enough that you can figure that out?
let me see if I can do it really fast.
Okay.
Okay. Hmm. Mm-hmm. Did you get 0.3136? That doesn't seem right.
No. What's the equation that you got? N is equal to what?
0.3136?
Well, what's the equation?
Oh, so I did four 400 times 1.960 divided by 50 to the second power.
Okay. Yeah, that's the right equation. You just must have just pressed something wrong on your calculator.
Huh. Hmm. I have the same answer. It's weird.
So the equation is sigma times z score divided by m. Just eyeballing it, sigma is 400, m is 50. So sigma divided by m is going to be 400 divided by 50, which is 8. And then you times that 8 by 1.96, which is roughly 2. So 8 times 2 is going to be 16. And then you square that. So you're looking for a bigger number than what you're getting.
Okay. Okay, so 245.8624.
Yes and no.
Okay.
You got the right number, but what's that number? What's the variable?
This is, so it says, so it can't be a decimal. So it
Yeah,
says round to the nearest whole number.
exactly.
That's going to be,
We're dealing with number of light bulbs, and you can't have 0.86 of a light bulb.
okay, so it's going to be 246.
Yes.
Okay. Huh.
And that's just pretty much an extension of what we did with questions 5 through 8.
Mm-hmm.
Um, it's just doing the reverse, which actually makes sense. The fact is, you're basically going around and you're saying what we're talking about confidence intervals. Large margin of errors and large confidence intervals aren't that useful. So this one they're saying, you know what, a confidence interval, I mean, a margin of error of 50 is totally appropriate. Let's
Mm-hmm.
figure out how many light bulbs we need to test. And that's actually a way that a lot of things go, a lot of studies go around, is that they first figure out what is an appropriate margin of error, then work backwards to figure out how many people or things or whatever they need to study, and then they do their study that way. That way, they already know what is the maximum number their mean can be off by from the mu,
Okay.
which makes sense.
Yeah.
You know what the weird thing about
Okay,
this is,
that
though?
makes
So you know what the weird thing about this is, though? And this is
sense.
just like totally random information.
What?
Light bulbs. I don't even know how my brother knows this. Well, he took a lot of stats classes, so I guess that's why. Light bulbs don't follow a standard normal distribution curve. They follow one of the weirdest curves there are. Because he was saying that what happens is light bulbs, like you would think that they would follow a normal standard, you figure that they would follow normal distribution, that some light bulbs would last longer than others. And
Yeah.
that's kind of the case. But he said if you look at it, it's actually, it's even hard to graph because it's so weird. He said with the way that light bulbs work, that if everything goes right, light bulbs will last pretty much indefinitely, like way long, so like 100 years or something. But the thing is, they're affected by other things. Most, basically, the biggest thing being the electrical wiring in our house.
Hmm.
And so he said, depending on the light bulb and depending on the housing that the wiring that it's in, it's actually a light bulb has the exact same probability of shorting every single time you turn the light on or off. So the fact is, it could, your light bulb could go out the first time you flip the switch
Hmm.
or the 1 millionth time you flip the switch.
Really?
It's the same probability every single time. So you have this really weird distribution curve where you have some going out on the first light switch and then some that are going on for years and years and years. Like it's a
Huh.
really weird curve.
That's interesting.
Yeah, it was really weird. Like, how the heck can that work? He's like, well, it's because light bulbs are simple and very sturdy. They're just glass surrounded by a filament. And he's like, the only thing that's going to go wrong with it, because they're sitting in the same place, you're not going to be breaking them unless you're stupid. He's like, it's involved with the wiring. And we discovered that it's actually pretty much it's different, the probability of it. So it's not like a 50-50 chance, obviously. Otherwise, you'd have to replace a light bulb like every fourth or so flip.
Yeah.
He's like, there's a small chance, like a 1% or maybe 0.5% chance that every time you flip it, it's going to do it. And that means some light bulbs are going to break on the very first switch, and some light bulbs won't break until the 1,000th. And some light bulbs are going to last a day, and some are going to last for years and years.
Hmm.
That's a super weird thing that they don't really understand.
Yeah, that's interesting. Huh,
Mhm.
I'm gonna like keep record of how long my light bulbs last now. Oh man.
So next question we have got. Oh, they're giving us mu here. Oh, and we've got a null hypothesis and an alternative hypothesis. So we're dealing with what we learned last week. So we're combining stuff.
Woo.
Okay. Oh, that's why my brother knew this. The mean salary of actuaries. Do you know what an actuary is?
Mm-mm.
They are the nerds to nerds. Like what nerds are to normal people, they are to nerds. Yeah, they are as to nerds as nerds are to normal people.
Oh, the ultimate nerds.
Yes, because actuaries aren't statisticians. Like
Hmm.
they're not theoretical statisticians. They are applied statisticians. So they understand the stats and then they apply it to real life things. So he was explaining it to me that actuaries, there's a lot of actuaries, big actuaries in like health insurance or life insurance.
Hmm.
Is like they'll figure out the stats and they'll figure out the probability. What's the probability of this dude dying in the next 5 years? And they figure out that probability, and then they decide, okay, this is how much we're going to charge him for life insurance. Like they take stats and apply it to the real world.
Okay, yeah.
He got too nerdy, so then he switched over to web development. So he got out of that. But that's how he knew about the light bulb thing.
Oh, that's
Oh,
your brother, man.
yes. Okay, so mean is 100,000. Sigma is 36,730. Okay, so our alpha is 0.05. So basically, we're saying we're testing to see, is our female actuaries paid differently than male actuaries? And we're not saying they're paid higher or lower. So what type of alternate hypothesis is this?
Not equal to.
But how is that represented on the distribution curve?
Oh, on the distribution curve.
Yes. So when we've got the applet out, if
Uh-huh.
our alternate hypothesis is not equals to, what does that look like and what's it refer to?
Oh, it's the middle. The middle is highlighted, I think.
No, you're having a little dyslexic moment. Do you
Oh,
remember
it's the two tails. You highlight the
there you
two
go, two
tails.
tails. Yeah. So
Okay.
just a vocab review from last week.
Okay.
Okay, so we have x, n equals 36, a sigma. So they're saying the sigma is for all actuaries, not just for men, so we can use that sigma. And we know our alpha is 0.05, so this is a roundabout. But alpha being 0.05 tells us what? What information do we get from that?
Um, The amount of uncertainty we are willing to accept.
Yes. So what does that tell us about our confidence? What's our confidence interval equal to?
Um, well, it says 95%.
Yeah. So we're dealing with a 95% confidence interval. So that gives us our
Oh,
z-score. Did it
uh,
say 95% confidence somewhere else? Oh, it did. Okay. Just in case it didn't give you that information,
uh-huh.
you can figure out your confidence interval from your alpha. So alpha in this case is 0.05, which
Which
is the
is
same as saying
5%, which is the same thing as saying 95% confidence interval.
exactly.
Okay.
So if they didn't give you your z-score down there, that's how you'd be able to figure out your z-score and what number you need to plug into the equation.
Okay.
So we have sigma, z-score, mean, and n. So we have everything we need.
Okay. So, okay. So, if it gives us all this information to find a z-score, do we really need to do because if it gives us the 95%, then that means it's giving us the z-score. So what do we need to do with all these other numbers?
So it's asking for our 95% confidence interval. So we have a mean of, so the 36 women that we sampled, we have now have a sample mean of 111,000. So we have a mean of 111,000, a z-score of 1.96, and an n of 36. So we need to first calculate the margin of error of our confidence interval.
Okay, so that's going to be did you get 11,998.
Mm-hmm. So that's our
Okay.
margin of error. And what do we do with our margin of error to create a confidence interval?
So we put the margin of error. Oh wait, say that again. What did we do?
So there's two parts of a margin. There's two parts of a confidence interval. We now have our margin of error, which is our interval estimate.
Mm-hmm.
So what's the second part of our confidence interval?
Oh, it's the point estimate.
Okay. So what do we do to get our confidence interval?
We find the mean.
We actually don't
Well,
need to. They've given us that, remember?
yeah.
111,000. So all we have to do is take 111,000 and then plus and minus our
Oh, margin of error.
there we go. Thank you.
Okay. Okay, which is let's see. Oh, 99,001 point 53333.
And round to the nearest whole number.
So it's gonna be $99,002.
Yes. Okay, and the high end?
And then that one's gonna be um 122,998. Well, 99.
Number there. Oh, there's two nines in there. Okay. Actually, I guess three nines after you round. Okay, so 122,999. Is that what you got?
Yes.
Okay, and then question 14 goes on to something irrelevant. I thought it was going to wrap this up. So how does this tie in to the null and alternate hypothesis?
Um, so this helps us determine whether the null or alternative hypothesis is true or not.
Yes, so how do we interpret this data? Would you say, are we ready to reject the null hypothesis, or are we going to fail to reject the null hypothesis?
Okay, so I would say, okay, let's see. I would say that we can reject the null hypothesis.
And why are you thinking that?
Um, I guess um because not I would like to just because 99,000 is really close to 100,000, so the null hypothesis is a little bit more than the low end of the the margin of error.
Okay, I like the way you're thinking. Um, but the way that we're dealing, so think about it this way. So
Mhm.
our null hypothesis is that all actuaries are paid 100,000 a year. So our null hypothesis is that female actuaries are paid 100,000 a year, right?
Mhm.
So what's our confidence interval?
Our confidence interval is um 11,999.
That's our margin of error.
Oh, 95. 95.
That's our confidence interval. What's the actual interval itself, though? What number to what number?
Oh, 99,000 to, well, $99,002 to 122,999.
Okay, so in layman's terms,
Mhm.
what does our confidence interval mean?
Hmm.
We are 95% confident what?
That these numbers are 95, we're 95% confident that these numbers that we got are within 11 11,999 of the population, the mu.
You're close. You're getting two concepts mixed up.
Okay.
So, what we're saying is that we are 95% confident that the average of all women actuaries makes
Uh-huh.
somewhere between 99,000 and 122,000. Does that
Yes.
make sense?
Yes.
So we're saying we're 95% positive that the number we're looking for, the the average salary of women actuaries, fall between those two numbers. What
Yes.
other number falls between those two numbers? There's a lot of them, but there's one I'm looking for specifically.
Um, oh, are you looking for um the mean?
So let me put it this way. We're 95% positive. I mean, not, yeah, we are 95% confident that the average salary of the female actuary lies between those two numbers, right?
Yes. Oh, but we're looking at 100,000.
Yes.
Yes.
So where do you jump off from there?
Um, uh,
You're making the right headway. So we are 95% confident that the salary average salary lies between those two numbers. We're
yes.
95% confident of that.
Yes.
What is the level of confidence that we have for any individual number between those two areas?
So the level of significance 0.05. Oh, how to tie into? Because in my head I was thinking, well, okay. So if we allow 0.05, um, it has to be less than 0.05 for us to reject the null. And if we got 99,000, is that less than 0.05?
We don't know.
Hmm.
But the thing is, what we do know is, we are confident that the mean salary falls between those two numbers, right?
Yes.
Another number that falls between those two numbers is the average salary, 100,000, right?
Yes.
So that means 100,000 falls within our confidence interval.
Yes.
So it falls within our confidence interval, and we are 95% confident that it is any of those numbers with those within that interval, but we can't say which number it is. So can we confidently say that it's not 100,000?
No.
Exactly, it falls within that confidence interval. So we're 95% confident that it falls within that interval, but we can't distinguish any given number and say, oh, this one's 99% confident. And
Mm-hmm.
so when our alpha is 0.05 and we have a 95% confidence interval, the 100,000 falls in there. So we're saying, you know what? 100,000 is just as likely as 99,000 or 122,000. We can't rule out 100,000 at this point.
Okay. So it doesn't really matter if it's on the low spectrum of it. It's
No.
still
If it was
possible.
below 99,000, so if
Mm-hmm.
it was $99,001,
Mm-hmm.
then we could say it is beneath our confidence interval. So we're fairly confident that women. Okay, let me rephrase this. Let's say so 100,000. Let's say our confidence interval instead of 99,000 to 122,000
Mm-hmm.
was 101,000.
Okay.
So it was 101,000 to 122,000. What
Okay.
happens there is our null hypothesis of 100,000 is now lower than our confidence interval. So we can say we are 95% confident that women make more than the average. Whether it's $1,000 more or whether it's $22,000 more, we don't know. We're
Mm-hmm.
just confident that they make more. And so, since it falls out of our confidence interval, we would then reject the null hypothesis and say women make more.
Okay. That makes sense.
Okay. I was actually really surprised. I was expecting question 14 to do a follow up on that to tie all the concepts together,
Yeah.
but she didn't. So I just wanted to go over that and make sure you understand how this ties into what we went over last week with alpha
Yeah.
and that kind of stuff. But does that make sense?
Yeah, that does make sense.
Okay. So
Yeah.
confidence intervals is basically kind of another way to do alpha. So if our
Mm-hmm.
alpha was instead of 0.05 was 0.1, then we'd have a confidence interval of 90%. And if our data, if our null hypothesis falls outside of our 90% confidence interval, then we
Mm-hmm.
reject the null hypothesis. You know, it's just
Okay.
another way to look at the data.
Okay. Yeah, no, that makes sense.
Because
Okay.
another way to look at this is, well, you understand it, so I won't go there. If it pops up, we can talk about it. But I think it would just confuse you at this point. Just trying to reverse graphs and that kind of stuff in your mind can be a pain. Okay, luckily we're ending on an easy one.
Yay. And this was straight from the reading.
Yes.
So okay, so it's all of the above.
Yes.
Nice. Nice, nice, nice. I will submit. And we can see how he did. Oh, we got 100. Woohoo!
And then, okay, so just beating a dead horse, question 12 and 13. You
Okay.
obviously know how to calculate the data. You got the confidence interval just fine.
Mm-hmm.
Just beating the dead horse, it makes sense how to interpret that information, right? Why we are failing to reject the null hypothesis.
Yes.
Okay, so
So
that does make sense to you.
yes, it has to be within that, or to keep the null hypothesis, um, it has to be within. Yeah, yeah, yeah. If it's outside, then we reject the null hypothesis and go to the alternative hypothesis.
Okay.
That actually does connect last week's lesson to this week's lesson. So
Okay. Yeah, I'm really surprised that question 14 didn't tie all that in together. Maybe she just threw that in to remind us of last week, and then the next lesson will be more two concepts. I don't know. We'll see. But I just wanted to make sure that was clear to you, so you weren't just calculating numbers and being like, why did we do a confidence interval when they're asking about alpha and that kind of stuff? But
yeah,
that's another way to interpret data, is we can use confidence intervals to reject or fail to reject null hypotheses. So
yeah.
that's how they're tied in together.
Okay.
Okay, we good?
Yeah, thanks for being patient with me.
Okay, no problem. I'll talk to you on Thursday.
All right, see ya.